First of all, let's watch our vulnerable application. It is in the buffer 1024 directory, and it is buff 1024.c. I open it with Notepad, and here is the source code of it. I just set the font size a bit bigger, and it's here. It's a very simple sample application only, so it doesn't do anything, only contains a buffer overflow. As you can see, it will start with the main function here, and it is a console application. It will require some arguments. The argc is the argument count, and the argv will contain the arguments. First, it will use some local variables. As you can see, it doesn't use anywhere. It's only here to simulate a real application, and the real applications use variables. And then it will call the function called function, and it will pass the first argument to this function. And as you know, the zeros argument is always the name of the file which is running, and the first argument is after the first space, and the second is after the second space, and so on. And our function is here. It will accept the input, and it will create a local variable called buffer, and the size of it is 1024 bytes. This is how it got the name. And then it will use the strcpy command to copy into this buffer, this 1024 bytes buffer, what it got. And as you can see, it is really vulnerable for buffer overflow because it does not do any size check. So if it will get more data than 1024 bytes, then it will copy in this case as well. So to be able to write the exploit, first of all, one must understand what happens when this program is running on the stack, and how is this application looks like in assembly. So I will open a paint, and I will try to draw some picture about it, and let's start. I will write the assembly code from the position when it calls the function with the argument v1, because as we can see, the vulnerability is in this function, so only this part is interesting for us. So I come here, and when I write this function call in C, it will compile to assembly something like call, and after that there will be some memory addresses, call 0x00, let's say 4010 FA, for example. I just write here something. What happens on the stack when this call is running? I draw here the stack. So as you know, the stack is a memory construction which goes to the direction of the lower addresses. It has some historical reasons. So when the computers, in the ancient time, when the computers was really just low amount of memory, not like today, when it is of course also low amount, but in reality it's huge. Then the program code was loaded to the bottom of the memory, and the local variables were stored at the top of the memory, because in this way I could use the memory most efficiently. So when I call a function, then after the function I will have to return, so there is this closing bracket, and at that position I have to return. So because I want to return after this call, somewhere I have to save the actual position. So for example, if I call this function, I jump here. Okay, or more exactly here. So I jump here, but here I want to return, so I have to save this address. This is what I have to do, and it is done on the stack. So practically it will save here the so-called old AIP, AIP, E means extended, so 32-bit, IP, it means now the instruction pointer. And because it is a 32-bit construction, the stack pointer, what we are going to write here, ESP, will change as follows. It was at some position, let's call it a 0 position, I will move it a bit closer. So this upper line is the 0 position. And because it is a 32-bit value, it will change to the -4 value, because as we will mention, the stack grows in the direction of the lower memory addresses. Great. Goes to the direction of the lower memory addresses. And now let's see what happens. Practically we jump here to this opening curly bracket. At the beginning of every function, there is some necessary stack adjustments, and how it is done, it depends on the so-called calling directives. There are many types of it. The most often used one, what I'm going to show you, is the cd-ecdl calling directive. Practically this calling directives tell you whose responsibility is the cleaning of the parameters, whose responsibility is to give back the original function, so the call, the local variables of it, and things like that. So I will show you the most often used one. In this case, the function, I do it a bit further because it's somewhere else in the memory. It's further from the call. There will be an instruction, something like that, push EBP. Push EBP. This push EBP instruction will put to the stack the old EBP value. I will draw it here. And it's going to be the old EBP. This EBP is the so-called base pointer. Sometimes it is called as frame pointer as well. So if you read, those mean the same. This frame pointer means the following. As you know, the stack is always moving because I create local variables, destroy them, call a function, whatever. So the stack pointer is continuously moving. So for a function, it is a bit more difficult to find its local variables by the help of this continuously changing stack pointer. That's why they use, of course it is not mandatory, but most of the compiler does in this way. The application uses the so-called EBP, which will point always to the beginning of the local variables. And from this constant value, it is simpler to find a variable, because you just have to use some constant shift and you will find the local variable. So I will push the EBP and the stack pointer will change to the value -8. -8. Now. Okay. The next instruction, what you are not able to see in the C code but represented by its open bracket, is the following: move EBP ESP. Move EBP ESP. So practically I entered to a new function and I set up the position of the local variables. The local variables now will start here. So it will be the position of EBP. I will do it. This is the EBP now. And after we set up the EBP, the next instruction is to create some local variable. It is done here. How we can create some local variable? You just create here some empty space on the stack where you are able to store any values. It can be done in assembly with the following instruction: sub ESP, comma, and here it should be written in hexadecimal 1024, so it is decimal 1024. In hexadecimal it is 400. And of course the 0x doesn't need in a real assembly. I just wrote it on this way for you to be simpler to read. Okay, what happens now in the stack? We will create some space here, like this, and the stack pointer will move to the position -1000, 32. Okay. And now comes the next instruction, the strcpy instruction. I don't know how it will look like, so practically I have no idea about it. I'll just write here some points, I don't know. It is practically unimportant for me. What is important for me, what it is going to do. What it is going to do, it will start to fill the stack from the bottom to the direction of the up. So upper direction, in this way. And this is why the buffer overflow can happen. Because as you can see, I fill the stack from the bottom to the direction of the top. So until I write here 1024 bytes, that's not important. If I write a bit more, for example 1028 bytes, then I will overwrite the old EBP. It will mean that when the function finishes, it will come back here. And because I have overwritten the old EBP value, this caller function will not find its local variables because I have overwritten the EBP, and most probably it will crash, or maybe I can use it to bypass some authentication or some input restriction, but most of the time we not do in this way. Our purpose in reality is to override the EIP, the instruction pointer, because if you are able to override it, then what happens? When the application here wants to return, here is the closing bracket, then it will read the address from here, I want to return to this position, but you as an attacker overwrote it, so it will return, instead of this real position, somewhere else, whatever position you want. And because you are able to control the IP, you are able to jump practically to a position where you are able to enter your own code and you are able to run an arbitrary code through this attack. So let's see how the application continues. Here is a closing bracket. The closing bracket practically is the opposite of the opening bracket, so I have to write the opposite of those two instructions here. It will be something like move ESP, EBP. So from the ESP, the stack pointer from here will jump up to this position. Practically, I destroy the local variables. Of course, those are not destroyed in reality because this memory range is not overwritten with 0 or something like that. I just moved up the stack pointer and this memory range can be reused. Practically this happens. It's something like a garbage collector, let's say that. And after that there will a push EBP instruction, the opposite of it going to be the pop EBP. So I write here the pop EBP. Means this, in the previous instruction the ESP was moving up here, and now because of the pop EBP the computer will take this value from the stack, so the EBP now points to this position. Sorry, the ESP now points to this position, and the Kali function will get back the position of its local variables beginning. And there is one more instruction which is required. I have to return to this position, and it can be done by a ret instruction. So here is a return instruction. One more thing what I forgot to mention, in case of some application, these two instructions, maybe you will find it as a leave instruction. It is exactly the same. So if you read that leave, practically it means those two instructions. They depend on the compiler. So this is how the stack working in this case. And for now you know how to attack this application. You have to do nothing else but enter 1032 characters and hopefully it will die. Let's check it. Let's test how the theory works in practice. First of all, I open a command prompt and I go to the buffer 1024 directory and call it buff1024.exe and give it some letter A as input. Nothing happened, of course. As you remember, the source code doesn't do anything important, but at least it was not frozen. There were no buffer overflow error now. Now let's try to add 1032 letter A as input. Of course, most probably you don't want to print it manually. So we are going to write we are going to write some Perl script to print 1032 characters. It will be the q1.perl script. Yes, I want to create this file, and the source code will be print in quotation marks capital E x 1032 and semicolon. File, save, exit. Let's try it. Oh, it works, there is no syntax error. Then I will redirect it to a text file. Open it. Copy paste and add it as parameter as the first argument. And let's run it. And there is a nice error message. Here is the close program. Let's go to the event viewer and see what did the Windows see from all those things. I come to the Windows logs, application logs. Here is the nice error message, and if I double click it, it was frozen at the memory address 4141414141. What is this 41? If I open browser and search for an ASCII table, here is the ASCII table, and if you find the hexa 41, it's here. This is, as you can see, the capital A. So, what happened now? The application started to write here the letter A's. Of course, it is a computer, so it is not able to write the letter A because it doesn't know what it is. It wrote here the ASCII code of the letter A, so 41, 41, 41, 41, and so on. And of course, here also the 41. And when the application arrived to this position and wanted to return, it will read from here the 41, 41, 41, 41, and it was jumped to the position 41, 41, 41, 41. It was of course just a random position. There it was most probably even not used, so it was frozen. Let's do another test. I use the upper arrow to call back this instruction and delete the last 1, 2, 3, 4 letter A, and instead of the A I will write here 1, 2, 3, 4 and then tab. Of course the application dies again. I check again the event log. Now I won't close it. Go to the Windows log, application log. Here is a nice error message again. And as you can see, here is the fault address 34, 33, 32, 31. If I check again the ASCII table, the 31, it's here, 31 is the 1, 32 is the 2, 33 is the 3, and 34 is the 4. So, there is one interesting thing here. I wrote the 1, 2, 3, 4. It's here, 1, 2, 3, 4. But here in the memory address, I read 4, 3, 2, 1. So the order is changed, exactly the opposite. This is because of the little endian ordering of the processor, of the Intel processors. So now we know that we are able to jump to any position, whatever we want in the memory, but we will have to change the order of the bytes in the memory address. So now we are able to jump anywhere. The question now is where to jump. And the answer is here on this picture, because now my input is here, the letter A's. So my purpose will be that instead of those letter A's, I will write some machine code, and I will want to jump to the beginning of this machine code, so practically here. As you remember, the stacks grows from the higher addresses to the lower addresses, while the program runs from the lower addresses to the direction of the higher addresses. So practically, I have to jump exactly to this position here at the bottom. So this is my target, this minus 1032. Okay, I want to jump here. But the question is, where is this position? Because all what I know about this position, it is minus 1032 to some starting values. And what is the starting values? The problem is that I have to write here to the old AEP an absolute address, because as you can see, this value will be substituted here. But I know here only the relative position. So what I have to do is to figure out the absolute position, and this is why I will need the debugger. So I go to the C drive, and here is the only directory. I open the only.exe, open the buffer 1024 file. Do not double click to it, only one time, because we have to give it some arguments. So here I'm going to copy those 1032 letter A's. So I copy it and paste it here. Opened it. I run it again. And as you can see, the application was frozen again at the position 41, 41, 41, 41. Okay, and now I want to find this position. What I have to do, I come to the debugger, and as you can see, this position is somewhere in the stack. So I have to check the value of the stack pointer. So I read the value of the stack pointer. This is the ESP. So I write it here somewhere 0x00 12 FD38. The next question is that where is this position? If it is down here, oh sorry, I drew it. So the question is that if it is somewhere here at the bottom, exactly somewhere here at the up, or somewhere in the middle. This is what I don't know. To figure it out, you have to recall that when does this application is frozen. If I come back here, the push ABP is running, so the application calls push ABP sub ASP 400 strcpy that's overwrite the stack, then move ESP EBP, pop EBP, and returns, and just after this return instruction, the application is frozen. So when the application frozen, then the ESP should point to the 0 position, so here. So what I know now is that this 0 position 0x0012 FD38, and I have the 0 position, this value, but I need the minus 1032, so I will use my calculator, change it to scientific, or in your calculators it is the programmatic view. And I will change this 12FD38 to decimal, because the 1033 is a decimal value. I subtract from it 1033, and it's equal this, but I need the hex representation of it. And this is the 12F930. and this is the bottom position. So 0x, 0, 0, 12, F9, 30, it will be the bottom. Okay. So now I have the bottom position, and if I come back to the OLEDBG, I see that this value can be found in the EIX register, F930. And it happens many cases. It happens because whatever every program is doing, practically they are just changing variables. This is what the program does, nothing else. The local variables are here somewhere, and most probably close to this red, the application was doing something with those local variables. So most probably one of the register, maybe AIX or some other register like ECX, EDX, EBX, ESI, EDI, points somewhere good position for me. Now it's a very good position because just exactly beginning. It's a very lucky situation, but even if it is a bit further, for example, if it points to this position, it will be good for me because I will fill this range with some space filling characters, unimportant, and I will start my code from here. So I just lose a bit space, but I have a register which points to the roof of my code. Okay, now just remember that the EIX points to the exact position where we want to jump. We will need this information later. Now we'll just memorize it. And I have the value, F930, and I close it. Close the debug gap. Let's try to jump now there. It will be our next code. So I create Notepad, a new file. It will be called as q2.perl. Yes. And the source code of it will be print in quotation mark capital E and print 1028 only characters, and in Perl the point is the concatenation, and I will add here my memory address. This is the 0012 F930, but as you remember it must be in reverse byte order, so I change it 30 F9 12 00, but if I were just leaving this way, then it is a string. So instead of the 30, it will write the ASCII code of the character 3, then the ASCII code of the character 0, then the ASCII code of the character F, and so on. It doesn't good for me. What I need is the hexadecimal 30. That's why I change it like \x30, \xf9, \x12, and \x00, and the semicolon to the end. There is one more problem here, the 0 or null byte at the end, because my application is written in C, and in C the 0 or null value is the string terminator. So practically the strcpy will finish the copying here, because the 0 is the string terminator. So this is all the thing what I'm able to copy. But it's not a problem for me because the strcpy will add the string closing 0 value to the end. So it will be just corrected. So now I'm able to use this 0 here because it is at the end, or I can just leave it out because it will be added by the C application. It will be much bigger problem if it is somewhere here, for example in the middle. Because if I calculate the 0 position, and if I get the value, for example F930, then the 00 is here in the middle, and because of that the strcpy will not even copy those values, and it's a problem for me because those values are required by me. What I can do in such a situation? In such a situation I have to change this value to a close one, for example a bit bigger value, then practically I do again the same thing. Instead of jumping exactly here, I jump somewhere here, and this small space is wasted for me. Of course it is not good, but at least I'm able to do something. So now we can use this value, and I file, save it, and let's generate the code. I use the q2.perl. It is printed. As you can see at the end, there are some special characters. The 0 can be recognized because the 0 is the 30. Others are something. I redirect it to another txt file. Open it. Select, copy, and add it as argument. Now it prints some different characters, but it shouldn't disturb you because the ASCII code of the character is the important, not the representation of it. So it's only that because of the clipboard copying, it is represented in different way. If I run it, it is frozen. Close the program, go back to event viewer, refresh it, and see the result. And as you can see, the application was frozen at the memory address 12FD63. 12FD63, it's somewhere here, up. Why it was frozen there? I was jumping here, and the application was frozen here. What happened here? Why it was not frozen there? Because my expectation for the application is to freeze here. It did not happen. What happened here is the following. The capital A is a valid instruction. It means this is the hexassertive. So the 0x41, 0x41 is a valid instruction. It is the increment ECX. So this is the instruction. You can even check it in debugger if you want. You just open the OLLI, open any application, for example the previous one, find here any instruction. I will choose this push AIX for example, and I edit it, binary edit, and I change it to 41. Okay, and this is really the ins ECX. So as you can see, it was a valid instruction. So what happened? I was jump here. There were a lot of letter A. What for the computer is the hexadecimal 41, which is a valid instruction, the increment ECX. And those increment ECX instructions were running. And here something happened because this memory address was containing some values. After it there was something. And it was running until there was some garbage, but it was not able to interpret as machine instruction, and then it was frozen. If you want to test that, definitely, if you jump to the correct position or not, then we have to modify a bit this code. I will write a new version of it, notepad. It will be the cube3.perl. Yes. And it will be print, and instead of the letter A, I will print the \xcc. The cc is the machine code of the int3 instruction. So 0xcc, this is the int3 instruction. This is the software breakpoint. So practically, when the application sees this instruction, then immediately halts. The debuggers use this kind of feature if you put somewhere a breakpoint. And I print, as previously, 1028 from those CC. So practically, here is the 1028, and after that comes the memory address where I want to jump. And where I want to jump is still the \x30, \x F9, and \x12 position. And I save this value. I'll save this code. I come back to the command prompt, run this q3.pl, I will get something, I redirect it to w3.txt, I open the w3.txt, select all, copy, and add it as argument to the buffer 1024 again. Now it looks like as different, but it's only a representation. Most of the time it shouldn't bother you. And press enter, and the application is frozen. If I go back to event viewer, refresh it, here is the error message, and now you can see the exact position, the 12 F930. So it is really proven that I jump to this position, so I arrive exactly to this position, and we were even able to see that the code here is really running. So now, because there is no data execution prevention and things like that, it was able to run without any problem. So our next task is to change those letter A's or those int3 instruction, some real machine code which does some good thing for us.